Welcome back to 14.8 Lagrange Multipliers, and like I promised, in this video we're going to cover the second case up here on distances. So what happens when you have to minimize or maximize a distance? And I said there was going to be a special twist, so here's the special twist. This problem comes from Godzilla, and the problem is the following. We want to find the point on the intersection. So actually, let me make sure I'm wording this correctly real quick. It'll take me like a quick second to pull up the problem. Should have done this beforehand, but oh well. All right. Here's the problem. Find the point closest to the origin on the curve of intersection of the plane x plus y plus z is equal to 1, and the cone z squared is equal to 2x squared plus 2y squared. Okay? And a lot of you guys are probably thinking right now, whoa, 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 what the hell is going on? Okay, so let's. I'll try to draw a picture. Maybe we can figure out what's going on. I'm not gonna promise it's a good picture, but essentially, what you have going on is you got a cone. All right, so you got a cone like this. All right, and here's your cone. Okay. So you got a cone, and then you got this plane, x plus y plus z equals 1, which is this green guy right here. You got the cone, you got the plane, and they intersect. Okay, so that's your plane, and then so it actually like extends, right, or something. I'm not exactly sure how this plane looks, but okay, let's do that. So you got your cone, you got your plane, and they're going to intersect at a curve that looks like that or something, right? And so we want to find the point on the curve that's closest to the origin. And this is an absolute abomination of a drawing. But hopefully it just helps, I guess, even somewhat with what's going on. So the red line, think of that as the intersection between the cone and the plane. Okay, so we've got to find the point of intersection, which is the red line. I keep on erasing stuff, I give up. There's some point here that's going to be the closest to the origin. And so how do we find this, and how the hell do we use Lagrange multiplier out of everything, every method that we have to solve this problem? So the idea is this, right? What do we need? What are the two components we need in a Lagrange multiplier problem? We need f, right, which is the function we need to minimize or maximize. Okay, it's called the objective function, if you hear me use that. So that's what f is. And then we need a constraint g, right? So what is the function? What is the function that I'm trying to maximize right now, right? What is f? Well, I'm trying to find the distance between a point and the origin, okay? And what is that function? Well, we know the distance formula between between 2 points, right? It's the square root of x minus 0 squared, right? Because 0 is the origin, plus y minus 0 squared, plus z minus 0 squared, right? So for any point x comma y comma z, so if you give me a point that's x, y, z, I plug it into this formula, and it'll give me the point closest to the. It'll give me the distance from that point to the origin, right? Okay, that makes sense. But remember what we have to do with f, right? When we use Lagrange multipliers, we use gradient f, and this with the square root is a massive pain in the ass to take a gradient of. So what can we do? What can we do to help us with finding f, or to make this gradient not as much of a pain to take? Well, notice, right, a square root if we consider just the inside of the square root, right? If that thing gets bigger, the square root gets bigger, okay? And if that thing gets smaller, the square root gets smaller, right? Just look at the graph of a square root graph. It's always increasing, right? It's always increasing. If as x increases, y is increasing. Always, right? So if this inside is increasing on a square root, then f is going to be increasing. So the point I'm trying to get at then is instead of taking the square root of all these guys, I can just let or I can just let my function f, the objective function, be equal to x squared plus y squared plus z squared, or simply put, just the inside of the square root. Okay. So I just take not equal to, but we don't want to choose this guy for f. Instead, we just want the inside of the distance function. Okay, and that's the trick with all distance problems, is that we only want the inside part of the distance function, or the distance formula, which is x minus 0 squared, well that's x squared, y minus 0 squared, that's y squared, z minus 0 squared, that's z squared, right? So when you ever have to find a minimum or maximum distance, in this point, closest, so the minimum distance, yeah, you want to check this objective function. You want to use this guy as the objective function. All right. So again, it's a coincidence that's x squared plus y squared plus z squared, because our point we're trying to calculate it to is the origin. So it's x minus 0, y minus 0, z minus 0. Okay. Don't just automatically be using this guy as the f, because it's going to change under different circumstances. If you're trying to find, let's say, if you're trying to find the point closest to 1, 1, 1, then of course you're going to get something different. All right, you're not going to get this guy. So, okay, so inside of square root of the distance function, sure. So what is g? So we spent all that time talking about f. What's our constraint g? And so this is where the little trick is. You're trying to find a point on both x plus y plus z equals 1 and z squared equals 2x plus 2y, right? Because when that cone and the plane intersect, that point is on both the cone and the plane, because it's on the intersection of these two surfaces. So g here, we actually have two constraints. All right, so this is why this problem is a little bit special. We're doing a Lagrange multiplier on two constraints, and so that's constraint number 1. This is constraint number 2. And what's the first constraint? Well, it's x plus y plus z is equal to 1, but let's move the 1 over. So now I've got minus 1 is equal to 0. Okay. So that's my first constraint. And what's my second constraint? Well, the second constraint is going to be the cone, and I'm going to say the cone has the equation 2x squared plus 2y squared minus z squared is equal to 0. Okay, so I move the z squared over to the right-hand side. Okay, so this is my problem. I have an f, a g, and an h. So what do I do when I have more than one constraint? Well, nabla f, right, or del f, the gradient of f, is going to be equal to lambda gradient g. Okay, makes sense. But now I have another constraint. Well, what I do then is I just add mu gradient h. All right, so mu is like, this is just another constant. It's like lambda. All right, it's just, I can't use lambda twice. I can say like lambda 1, lambda 2. That's fine, but I'm just going to call this constant here mu. Okay. All right. So now I can go finding the Lagrange multiplier, and notice this problem, right? It's simply just find the point closest on the origin on this intersection. So unlike the previous video where we had an interior where we had the check, there's no interior here, all right? I'm on the boundaries. I'm only on the boundaries, right? Which is the intersection of the cone and the plane. So I just jump straight to the Lagrange multiplier problem, all right? So if you don't have like a closed region, you don't have to check any of the partial stuff for critical points. Okay, So hopefully that made sense. Again, I'm only on the boundary because I'm on an intersection here. Whenever you have to find like minimum or maximum distances, just jump straight to Lagrange multipliers. You don't have to worry about the stuff up here with the interior part stuff, okay? Because again, different problems have different methods. In the previous example, we had an interior region, right, with this circle and the inside, but here we're just on the boundary, okay? So we jump straight to the Lagrange multiplier, which in our case is a special two-constraint Lagrange multiplier. All right, so what's del f? Well, f is x squared plus y squared plus z squared, so the gradient is 2x, 2y, 2z. All right, that's equal to lambda times the gradient of g, which is x plus y plus z minus 1 equals 0, so the gradient of that guy is actually 1, 1, 1, and then plus mu times, and then this should be 4x, 4y, negative 2z. All right, so this is my Lagrange multiplier. So now what do I have? Well, I have 2x is equal to, all right, lambda times 1, this first entry, which is 1, all right, plus mu times 4x, so let's do 4x mu, right? And then I got 2y, so now I got the second components are all equal to each other. Well, that's 1 plus 4y mu. And then finally, I got the third components that need to be equal to each other. So that's going to be 2z is equal to oh wow, I've been writing 1. These should all be lambdas here, right? Because it's lambda times 1, so it's lambda. And then minus 2z mu. All right, so now I got 3 equations, but I got 4 unknowns. Or do I have 4? I have 5 unknowns. Wow, right? 1, 2, 3, 4, 5. I have 5 unknowns. So where are my other equations? Remember, you can always use the constraints, right? And so what are my constraints then? Let's say x plus y plus z is equal to 1, and I also got 2x squared plus 2y squared equals z squared. All right, so these are my 5 equations now. I got 5 unknowns, so I can solve the system. This is a little difficult, so how do I solve, what's a good way to solve the system? Usually, it's a good idea to actually find what x, y, and z are going to be, all right, and in terms of other variables. So for example, how do I find what x is going to be? Well, let's subtract 4x mu from both sides. I get 2x minus 4x mu is equal to lambda, right? And now, if I factor out an x from the left-hand side of the equation, I get x times 2 minus 4 mu is equal to lambda. And then I get x is equal to lambda divided by 2 minus 4 mu, right? Fair. And this video is running a bit long, so to save time down here, you do the exact same thing with y and z, right? So you get 2y minus 4y mu, all right, is equal to lambda by subtracting 4y mu from both sides. And then if you follow these steps, exact same steps, I'm only skipping 1, you'll get y is equal to, well, lambda over 2 minus 4 mu, okay? And then for z, do this exact same thing as I did with the previous two, and you should get z is equal to, and I'm actually only skipping 2 steps, lambda divided by 2 plus 2 mu. All right, and what do these 3 equations here tell us? Well, I can see right away that x is equal to y, right? So I can see that x is equal to y, and then z is essentially by itself. So where do I go now? Where do I go with this knowledge of x, y, and z? Any ideas? Where do I plug these guys into? Well, it seems like the easiest one to plug these guys into is going to be this constraint right here, right? So if I plug in x, y, and z, I now get lambda over 2 minus 4 mu plus lambda over 2 minus 4 mu, right? Because that's x and y. And now I plug in z, lambda over 2 plus 2 mu. That's equal to 1. All right? And, okay, so where does this take us? Well, I get what? If you add this up, this left-hand side up, I get I get lambda divided by 1 minus 2 mu, all right, because these guys essentially become 2 times lambda over 2 minus 4 mu, and they can factor out a 2. So these two guys become this guy right here, and then plus lambda over 2 plus 2 mu is equal to 1. And actually, for now, we're just going to have to leave it there because I have 2 unknowns, right? Can't really do anything about that. So now what? Well, now I have one more equation I haven't used, right? I haven't used this guy. So let's plug in x, y, z into this guy. And it looks a little crazy, but believe me, it'll work out. You just have to persevere through this. So, okay, so let's write this further down a little bit to give us a little bit of room. So let's say I got 2x squared plus 2y squared is equal to z squared, right? So remember what x and y are. X and y are lambda over 2 minus 4 mu. So I get 2 times lambda over 2 minus 4 mu squared plus 2 times lambda over 2 minus 4 mu squared, since x and y are the same thing, is equal to z squared. That was lambda divided by 2 plus 2 mu squared. Lambda divided by 2 plus 2 mu. All right, squared. Okay. Now what? Now, oh, missing a squared there. Now, you'll notice that I can just add these two guys up, right? And I get 4 lambda over 2 minus 4 mu squared is equal to lambda over 2 plus 2 mu squared. And yes, I do have a mistake here, right? This squared right there, right? There was a square term right here. That was a mistake, so you should erase that. So I got 4 times lambda divided by 2 minus 4 mu squared is equal to lambda divided by 2 plus 2 mu squared. Well, I can actually solve for this somehow. And what do I do? Well, let's take the square root of both sides. And this actually works out nicely. Because what's the square root of 4? Well, it's 2. All right? What's the square root of this guy squared? Well, it's just that term. And then the square root of the left-hand side, well, it's just the guy not squared. So lambda over 2 plus 2 mu. Okay. And what do I want to do now? Well, let's see if I can solve for something. Well, yeah, I can, right? Because 2 cancels out here on the left-hand side. So I get lambda over 1 minus 2 mu is equal to lambda over 2 plus 2 mu. Ah, this is exciting, right? How do I solve for this? Cross multiply. I get lambda times 2 plus 2 mu is equal to lambda times 1 minus 2 mu. Divide both sides by lambda. 2 plus 2 mu is equal to 1 minus 2 mu. And now we actually recover what mu is, and you'll see that mu is equal to negative 1/4. All right? So mu is equal to negative 1/4. That's a big deal, because now up here with this guy, I have mu is equal to negative 1/4. So now I got lambda divided by 1 minus 2 times negative 1/4 plus lambda over 2 plus 2 times negative 1/4 is equal to 1. Well, that's equal to lambda over 3/2 plus lambda over 3/2 is equal to 1. Okay? And now I can solve for lambda. And what is lambda? Well, multiply this entire thing through by 3/2. You get 2 lambda is equal to 3/2, right? And lambda then is equal to 3/4. So I got mu, I got lambda, there's mu, there's lambda. What can I do now? Well, I can find x, y, and z, right? Because x, y, and z only depend on mu and lambda. So what is x? Well, lambda, right? X is lambda over 2 minus 4 mu. Lambda is 3/4. And mu was negative 1/4. Okay? And so now I've got 3/4 divided by looks like 3 on the bottom. And that means x is 1/4. Well, y is equal to x, as we can see right here. They're the exact same equation. So y is equal to 1/4. And then z is equal to 3/4 divided by 2 plus 2 times negative 1/4. Right? So now that's 3/4 over 3/2. 3/2? 3/2? Yeah, 3/2. And that's equal to 1/2. So I got myself a critical point. And I actually made a mistake down here. What's the mistake? What's the mistake down here? The mistake down here essentially is I took a square root, right? So this guy could be minus, this guy could be minus. That actually doesn't change anything. This is actually fine for now. Okay, so this is what I got, and okay, so I got 1/4, 1/4, 1/2, and I want to make sure that that fits. So I didn't actually make a mistake. I thought I made a mistake with the square root, but it actually doesn't matter. So be careful with the square roots because you get plus or minus. This guy's plus or minus. So I guess technically speaking, mu can also be a positive 1/4 as well. So yeah, I think this is fine. This is fine. Okay. Anyways, let's go back here. So here's our point. All right, I got one critical point now. 1/4, 1/4, 1/2. Okay, so that's a critical point, and now we have to consider what assumptions did we take. Right? What are some liberties that I took here? Okay. Right. The first liberty I took is that I assumed mu wasn't 1/2, right? Because if mu were 1/2, this denominator would be 0 and be undefined. So that's one thing I need to take into account. I need to take into account mu equals 1/2. So what happens in the case of mu is equal to 1/2? Well, we copy down these three equations right here, and we plug in mu is equal to 1/2, I get the following. I get 2x is equal to lambda plus 4x mu, but mu is 1/2. All right. I get 2y is equal to lambda plus 4y mu, which is 1/2. And then I get 2z is equal to lambda minus 2z mu, which is 1/2, right? And again, why am I considering mu is equal to 1/2? Because right here, right, we got 2 minus 4 mu in the denominator. Well, if mu were 1/2, the denominator would be 0, and I would get undefined x and y coordinates. So we need to make sure that mu is not 1/2. So we check mu equals 1/2, and what do I get? Well, on the right-hand side, this becomes lambda plus 2x. Whoa, glitch. This becomes lambda plus 2y, and this bottom one becomes lambda minus z. And do you see what goes wrong? What goes wrong? Well, now I have 2x is equal to lambda plus 2x. So if I subtract x from both sides, I get lambda equal to 0. All right. And now here, I got 2y is equal to lambda plus 2y. And if I subtract that, I get lambda is also equal to 0. Okay. And now at the bottom, I know lambda is equal to 0. So then 2z is equal to negative z, since lambda is equal to 0 from up here. And, well, the only way this can be true is if z, right, so this is actually like coming down from there, and then these guys are like that. Well, z has to be 0 in order for this relation to hold. Okay, so if I know z is 0, right, then what the hell are x and y? Well, x and y then have to satisfy both both constraints simultaneously. And it has to satisfy this guy, and it has to satisfy that guy. Well, x plus y minus 1, no, wait, x plus y has to equal 1, right? So so since z is 0 now, So we found z is 0. So x plus y has to equal 1. But simultaneously, since z is 0, what's my other constraint? Well, my other constraint is this guy right here, right? My other constraint is 2x squared plus 2y squared has to equal 0. And it's impossible. There's no solution here, right? Because this automatically says that x and y are 0, but then that doesn't satisfy x plus y equals 1 if x and y are 0. So there's no solution in the case of mu equals 1/2. What's the other problem? The other problem occurs when, here's the other denominator. I got 2 plus 2 mu, right? Well, what if 2 plus 2 mu were 0? So what if mu were equal to -1? Okay, so from z, can't have the denominator being 0. So mu is equal to -1 is the other problem that we need to check. And what happens here? Well, I get 2x is equal to lambda plus, oh boy, I need some calibration here. 4x mu, which is -1, right? 2y is equal to lambda plus 4y mu, and 2z is equal to lambda minus 2z mu. And you guys see what goes wrong? Well, if we carry out on the z's now, I get 2z is equal to lambda plus 2z, which means lambda is equal to 0. All right. Okay, lambda is equal to 0, cool. But what ramifications does that have? Well, now I get 2y is equal to 4y, or -4y, right? Because lambda is 0. So now I get 2y is equal to -4y. When's the only case that's ever true? Well, y is 0. And I get 2x is equal to -4x, right? Because lambda is 0. And that only happens when x is 0. So now I know x is 0, y is 0. Okay. Well, remember what my other two constraints were. I got x plus y plus z is equal to 1. I got 2x squared plus 2y squared is equal to z squared. Well, if x is 0 and y are 0, then 0 squared, 2 times 0 squared plus 2 times 0 squared is equal to 0. Right? So that means z squared is equal to 0, which implies z is equal to 0. Right? But up here, it implies z is equal to 1. Okay? And because of this, x equals 0 and y equals 0, I got z is simultaneously 1 and 0. Can't really have that happening. So because of this, there's no solution at these points, right? At x equals 0, y equals 0. There's no solution to this system of equations. So when mu is -1, there's no solution. When mu is 1/2, there's no solution. And when and the other way we solved it, we solved this for this critical point. And you know how I was being nervous about this guy being plus or minus and this guy being plus or minus. It's fine because this cross multiplication right here, right, where I took this guy, multiplied it here, this guy multiplied it here, that takes care of any sign problems that we have. So yeah, actually there's really no worries here that we have to deal with. Okay, so that's fine. And I get this point, 1/4, 1/4, 1/2, and that's the only critical point. So now let's plug it in to the distance function, x squared plus y squared, right? So I'm maximizing x squared plus y squared plus z squared, but my distance function is still the square root of x squared plus y squared plus z squared, right? So this is the point of the minimum, all right? This is the point where the minimum distance is located. Okay, that's the point where that's closest to the origin. It's that point. If the problem asked me to find the distance as well as the closest point, then the distance is going to be equal to the square root of 1/4 squared plus 1/4 squared plus 1/2 squared, and that's equal to the square root of, let's say, if this becomes 1/8 plus 1/4. Right? And that's equal to root 3/8, which is the distance, right? Remember, my objective function, the function I'm trying to minimize, is x squared plus y squared plus z squared, but the distance function is still the square root of that guy. And the only reason why I can just look at the inside of the square root is because the square root is always increasing. So if x plus y plus z is bigger, then my distance will be bigger. And if x squared plus y squared plus z squared is smaller, then my distance will be smaller as well. Okay? So, wow, what an involved video. Over half an hour devoted to solving this one problem. I really hope I didn't make a mistake. I don't think so, because this is a book problem and my answers are consistent with the book. So this is what you expect out of a distance problem where you have to use Lagrange multipliers. This is also a very good example for a double constraint Lagrange multiplier as well. Okay? And that's it for Lagrange multipliers. Oof, I don't want to talk about these guys anymore. So let's move on to 15.1. Where 51 and 52, we're going to talk about integration now. We're going away from gradients and derivatives for a little bit. We'll come back to them in 16.